Hi, my name is Matt Spencer. I'm a principal software architect in Arm's automotive and IoT business line. I'm here today to talk to you about service-oriented architecture for autonomy and autonomous solutions, and why it's important in the verticals that we're looking to drive business into. So first of all, just a quick overview of what service-oriented architecture is. I'm going to call it SOA from now on because it's a bit of a mouthful. But SOA is basically a design methodology that helps you to break down large and complex solutions into smaller, manageable chunks. These chunks can then talk to each other through standard interfaces, traditionally over a network backbone, but as long as they have a defined means of communication, that's fine. But by building out a service-oriented architecture, it enables you to, as I say, break down your problem, but it also then you end up with functional components for your solution. And these functional components are easier to develop, they are easier to test, and they are easier to deploy. So for instance, you will have a documentation of what the inputs and outputs to each of your blocks are, which means it's easier to place them into a test and a continual testing and continual deployment framework that's going to enable you to create better software. So that's a very high level overview of SOA. So SOA in itself depends on standards across the board of every area that it touches. So in development, in deployment, and in the lifecycle management of the workloads that you're deploying. And these standards give you, from a development perspective, a consistent way of building and deploying your applications. So that's a great thing from the outset because it enables you to standardize the way you onboard engineers into your team. There's a clearly defined way of working. You have that CI and CD baked in from the outset, and it enforces best practices. So breaking down those large complex problems into smaller, more manageable ones is just plain common sense. The deployment of the workloads is also something that gets covered by SOA. So how you deploy that workload to the target device, how you check the integrity of that workload. So, do I trust where it came from? Has it been tampered with on the way to getting here? And then how you access the system resources that are available to it. Now, do I have access to the file system, to networking? Can I speak to other nodes on that same system? And the third pillar here is the lifecycle management. So how you launch the workloads, what are those runtime requirements? And we'll talk about this a bit later. So, do I have real-time requirements for my application? And again, how you physically access those system resources rather than if you have the permission to access those system resources. So these are all standards that help us to create those workloads. So let's move on to ask the question, why is SOA important in autonomy? So firstly, we're going to give a definition of the problem statement. So when you look at autonomous solutions, software is becoming increasingly more complex. There will be talks of millions, billions of lines of code going into a level 5 autonomous vehicle. And that software is becoming increasingly complex and increasingly expensive to develop. Then when you start to look at how workloads are deployed to the final solution, you tend to get a BSP from your silicon vendor, and that BSP has a particular way of working. So it'll expose interfaces, it'll have accelerators available to it, specific drivers for those components. But the problem then becomes is that those millions of lines of code are now linked to a specific BSP and a specific way of working, which means that your workload is no longer portable to other solutions or even newer versions of the silicon that's coming from that particular silicon partner. And that's creating huge problems across the industry for us. I've spoken to a number of OEMs in the automotive space who have said that it is cheaper and simpler for them to throw away their code and start again when they start a new production and try then integrating software on that new platform. And we cannot, that's not a sustainable position going forward. So now that software is becoming the primary commodity, we really need to understand how we can use standards to help us reuse the maximum amount of the code that we're building, and that's where some of these concepts of SOA come in to help us. Okay, so I'm going to take a step back for a second and talk very briefly about Project Cassini. Project Cassini is being discussed in a number of other presentations, so I'll only skim it briefly here. So a number of other presentations here at DevSummit, so you go find those out and learn more about those. But Cassini is coming from the infrastructure business line within ARM, and it's trying to do for edge devices what the ARM Server Ready program did for infrastructure in the mega data centers. In that it standardizes the way that the platform looks to OSVs, so commercial software vendors in this space, so that they can write one version of their OS and deploy it to any server-ready compliant platform. So Cassini is doing the same thing, but it's doing it for edge nodes in the network, and they're basically taking the server-ready program and creating something that ARM are calling system-ready, which is looking now at multiple verticals within the ARM ecosystem and how we can standardize the view of those systems. Adding to that some elements of security, so PSA as a security architecture and technologies like Parsec to enable us to bring those security methodologies into the applications that we're building. And it's also then building on cloud native, because everything is going cloud native these days. And again, this is part of the SOA view that we're looking at. So what we want to do with this, in terms of the SOA for autonomy, is build on some of those concepts of Cassini, but bear in mind that when we're working in automotive and autonomous domains, we have different requirements. We have subtly different requirements, and those come around things like mixed criticality, certification. There's a number of different areas where we differentiate. But what the project here wants to do, and I'm going to keep calling it the project because it doesn't have a name, an external name yet, and we'll cover that at the end of the presentation here. But what we're trying to do is create an open source and standards-based development platform that's based around Cassini at the base, and then adding these additional features to enable people to start developing software for this platform as soon as possible. We also are collaborating with a number of ARM partners at the moment. So this comes from commercial software vendors, tier ones and OEMs, and the silicon providers in the space to build this incremental solution-focused development platform. And it needs to be incremental because at the first step of this project, we're not going to be able to solve all the problems in one go. We also want to be working in the open, in the upstream projects that are being consumed by this platform, to enable them to move towards compliance with the standards that are required in the automotive and autonomous space. The fourth point here is that we want to work with commercial software vendors, because what we're doing is we're building an open source reference platform to enable the rapid development of workloads. And those workloads can be compliant with standards like ISO 26262, but the open source platform that sits underneath it isn't necessarily going to be of that same quality to enable us to deploy that platform to the target solution. So we want to work with commercial software vendors to enable them to have drop-in replacements for base parts of the system, so that we can take the workloads that the OEMs are creating, the commercially supported software from the OSVs, and take that to market. The fifth point is the most important here, is that we're working to solve the problem of workload portability. And the workload portability is hugely important because once we've invested in a functional block on release 1 of our solution, we want to be able to take that functional block and deploy it to future versions without having to reintegrate it at every single point. So this platform is hugely opinionated about how we deploy and develop workloads. And the aim, that the last line here, is that we really would like to see this become the end of the BSP, because the BSP has been creating pain points for us over years now, because it ties us to a particular way of working. So what we want to do is build on best practices as well. So we've already talked a little bit about cloud native and the DevOps processes that exist there. So leveraging things like containerization to package the workloads seems like a great idea. And the way that the container ecosystem is built up, again, around standards, enables us to pick and choose the right technologies in that container space to meet the requirements that we have for our final solution. It also brings in some robust DevOps workflows, so we can do that attestation of the container images themselves. We can validate where they've come from. We can check at every point of that workflow that it is exactly what we expect and what we want to deploy. And there's also strong testing and validation that sits in there. But on the right-hand side here, we also want to standardize the way we get access to system resources. So part of the big part of the problem is that if I have a workload that needs to access a GPU, for instance, traditionally I need to have that GPU driver as a part of that workload. And as we all know, GPU drivers are hugely tied to the underlying IP that's implementing the GPU. So that workload is no longer portable if I have to have the binary driver for a specific GPU. So what we're looking at doing is extending Cassini, as I've said, and understanding the modifications that need to be in the system-ready program for our workloads, but add things like para-virtualized access to accelerators in the platform as well. And the last point here is that we want to be working with domain-relevant user space libraries. So, for instance, if you have a BLAS library that needs access to your GPU to accelerate, we want to work with that BLAS library to integrate the concepts of the para-virtualized access so that we can so that you can choose the right library for your particular solution, and it will seamlessly make use of the underlying capabilities of your platform. Okay, so we're going to go through a quick overview of the high-level architecture of how this platform looks at the moment. And everything we're going to put inside this dotted box here is going to be part of what we would like to see in the reference stack. So we build on the foundation of the project Cassini. So on the partner silicon, we have the Cassini firmware, which brings us the system-ready boot capabilities. We have PSA, we have Parsec, we have other parts of that system. But on top of that, we'll be adding a hypervisor. And the reason we bring a hypervisor into scope, a type 1 hypervisor, is that it enables us to manage the compartmentalization of the system resources much easier. So we can make use then of an orchestrator to partition the platform in a way that makes sense for the particular workloads that we want to run. And then we bring those container workloads into scope as well. And those container runtimes are where we're going to be deploying the application to. So then what we need to do is we need to add the SOC specific parts to the system. And you'll notice that the dotted line goes behind this box because this is actually not a part of the reference stack, but it's an add-in to the reference stack that brings in the drivers and the platform-specific capabilities. But what we're showing here is that we intend to use technologies like VirtIO to give you para-virtualized access to those drivers rather than requiring you to have this BSP in every single one of your container runtimes to give you access to those platform resources. So that's a hugely important concept here, is that everything in that dark green box in the background, that's all standard. And everything that comes in that orange box is going to be different depending on the SOC that you're working on. And then we look at what we're running on top of those container runtimes. And these are the workloads. These are the important bits. This is where we are differentiating our end solution. And what we're showing here is that we want to bring these concepts of mixed criticality into scope as well. And we think we can manage that through the container runtimes and the use of the hypervisor to make sure that the system resources have been split suitably so that we can hit the A or B, in this case, or A or D requirements of those workloads. Those workloads will be derived from the ecosystem or from, like I say, from the OEMs in this space. Okay, so when we look at how we develop for this, just to show how standards-based this whole process needs to be, me as a developer now, the way I work with this platform is to work in a standard containerized way. So here I'm showing a very basic Docker file that says from my base platform, which is part of this program. So it'll define what's at that base level with the VirtIO capabilities. And I'm saying here, from that VirtIO base, we also want to have the concept of a safety island and access to that safety island. I then install my development requirements, so the compilers and tool chains. I build the workload, and then I tell the workload how it wants to be executed. Now, it's important to say that this isn't a multi-stage Docker file. This is here for simplicity. You wouldn't do it this way in deployment, because you will end up with all of your compile time and all of your tooling still in that end container that is not actually required there. But that's out of scope really for this conversation. So let's go quickly then through a worked example. I'm bringing some real technologies into space. So we're back to that reference stack. We have a base level of Cassini again, and we're going to bring in Zen as a type 1 hypervisor. And the reason we choose Zen is quite simple. It's a mature open source technology that has a vibrant community around it, but it's also cognizant of functional safety requirements, and ARM are working with the Zen community to try and understand what would be required to take the open source project through an ISO 26262 accreditation. So on top of that hypervisor then, we want to think about how we're going to run our orchestration. So the default orchestrator that's used in the cloud today would be something like Kubernetes or K8s. But for our requirements, that is quite a heavyweight way of working. It brings in too many runtime requirements for us to work in an embedded environment that these automotive solutions are. So we'd intend to use something like K3s. And K3s, again, is a standards compliant orchestrator from Rancher. It's an open source project that we can then work with within the OCI to work on the standard specifications, but then also as an implementation in K3s to explore the ideas of mixed criticality workload deployment and what that looks like to the orchestrator. We then start to look at what the container runtime should look like. And here we're bringing in another new technology that's part of the LF Edge project called RunX. Now, RunX is in early development, but it is an OCI-compliant container runtime that runs bare metal on a Zen hypervisor. And this is important because it minimizes the amount of code that I have between my workload and the underlying SOC, the underlying silicon. Another interesting thing to point out here is that I could take that RunX kernel and I could derive that from something like the ELISA project that again is looking at how you can take the Linux through a functional safe certification process. And all that kernel now needs to have is the VirtIO interfaces and enough functionality to run a container runtime. So actually in that vertical slice, in that RunX container now, I have the bare minimum amount of a kernel that I need to run my workload. We now bring back in this is the same driver domain that we had in the earlier slide that brings in the platform-specific drivers and the VirtIO interfaces. So I don't need to really cover that again. And then we look at an example of what that workload would be. Now here I'm pulling in AutoWare as an open source autonomous drive platform. We would work with the AutoWare community as we are today to implement that workload against the VirtIO interfaces. Now, the important thing here is that when we get to that point, that application will be binary compatible with any other ARM platform that adheres to this methodology, and that's really important. There's an understanding amongst the OEMs that there will be a performance hit for doing this. But everyone that I have spoken to says application portability to them is more important than the performance. And as long as the performance can be contained, then that's all well and good. And then we can go and deploy other workloads here. So we've got Android Auto for IVI and digital cockpit. We've got vehicle to infrastructure style services and OEM services. And all of these are binary compatible. They can be deployed to any solution that conforms to this system. So that's the project in a nutshell. So what are the next steps for us here? So the first point is that we, as ARM, are already having talks with OEMs, with tier ones, with silicon partners and commercial software vendors. But we want to bring those all together in an open foundation that's going to enable the development of the standards or the adoption of the standards that already exist, and also the development of a reference implementation of the stack. I was hoping we'd be in a position to launch this here at DevSummit, but we weren't quite able to get to that point. But we would love to have you guys involved in making sure that we're building the right solution here. So if you are interested in joining or want to get involved, please reach out to us and we'll make sure that you're included in any future communications that we're having about this. And on to the conclusion. What we're trying to do here is adopt the best practices that exist in other domains and bring them over to the autonomous and automotive domains to help solve the increasingly complex software complexity problems that we have. But we want to do this in a way that enables ecosystem partners, OEMs, the tier ones, the silicon partners, all to benefit from a compatible platform that enables them to differentiate with the underlying implementation, but doesn't break compatibility with the workloads that the OEMs are trying to deploy. These systems are getting more and more complex, and the simpler we can make the platform from a developer's perspective, the better chance we have of landing high quality software as early as possible. So thank you very much for joining this presentation. I hope you've enjoyed it, and I hope to see you all in person at the next conference. Thank you.
Hello guys, thank you for joining. Today you'll have to excuse the way I'm dressed. I'm going off to referee a rugby match straight after this presentation, so it's one of the benefits of working from home rather than being there in person with you guys. If you've got any questions, please raise them up. We have one here already, and I will try and do my best to answer them all in the time that we've got. So the question here is, how does the stack address scaling challenges in all IP flows in layers 4 to 7 in a cloud topology? What benchmarks or virtual test beds do you recommend? Well, it's an interesting question, but it's not really the domain that we're trying to solve with this project. So, like I say, I was hoping to have a name for it so we could actually speak about a concrete thing. What the project is trying to look at actually is constraining the problem of workload portability. and then trying to solve the underlying technical issues that we have with the performance and the integration of those workloads. We can take a concrete example of this. Google with Chrome OS have been using VirtIO GPU and Virgil to do graphics streaming in Chrome OS. And they've been working with open source collaborators in that space to solve the performance impact of streaming graphics commands over an API rather than directly into the GPU. And their primary use case is gaming. And where they started from in the early days was a functional but not performant system. But once you've decided on a technology and then you're working to solve the performance problems, they went from having a non-performance system to a highly performant system in a short measure of time. So that's what we're trying to look at here. These questions that you raised, Getty, will be covered, but we'll find out where the problems are and solve them as and when they are encountered. So the next question is from David, which just says outfit change. I'm dressed in my refereeing outfit because, like I say, I'm going to referee a rugby match in a minute. So you don't want to look down here because I've got my short shorts on as well. So I'll save you and me the embarrassment of that as well. Max Turner, where, if at all, do you see adaptive autosar in this picture? That's a very good question. And all along, we've tried to keep ISVs and OSVs involved in the conversations we're having, because what we want to make sure is that when we've decided on the right standards and technologies that we're going to use to deploy the workloads, we in the foundation want to build an open source reference that bootstraps development. But what we're not saying is that reference implementation is suitable for going through an ISO 26262 process to then be deployed in real products. That's not to say you can't do that if that's what you want to do. But what we would like to see, and the encouraging stories that we're having from the OSVs is that they're interested in adopting this methodology, is for them to have drop-in replacements for every part of the underlying system that we saw before that sits on top of Project Cassini, so that the workloads stay consistent. But the middleware layer that you've got is then from a commercially supported, functionally safe origin. So it's in that space there that we could see adaptive autosar working as that middle layer. But if you wanted to then run it as a workload on top, we would then have to look at how we can containerize the capabilities of autosar and how we integrate that into the platform. So it's all about creating standards at the interfaces that we want to communicate over. So a question from Ahmed: how do you see the integrity of this solution with adaptive autosar? I think I covered a little bit of that before. So what this isn't trying to do is not trying to compete with adaptive autosar, and it will adopt parts of the autosar standards that are sensible to do so. But it's looking also to be deployed in more than just autonomous domains as well. So we see this being relevant in any place where mixed criticality app deployments are required. Industrial robotics at the edge of the network, anywhere where you need mass deployments of functionally safe and portable applications is where we see this running. So autosar can be a consumer of this, or it can be part of that base layer. So I hope that answers. So the difficulty thing here is that I can't see if I've answered any of your questions at all. Question from Fake here: will there be an OpenCL integration with the stack to address hybrid processing platforms, including CPU, GPU, and FPGA? And that's a really interesting question, because absolutely yes, we need to be abstracting all of the accelerators. So I've already mentioned things like VirtIO GPU for the GPU domain. One thing that we want to do within the foundation is identify the gaps in the VirtIO specification, come up with a functional implementation of that para-virtualized interface, and then work at getting that standard adopted within the Oasis community. Okay, I think I've got to the end of the questions there. Thank you so much. I've got about 10 seconds left, I believe. So thank you so much for joining the talk. As I said, we're launching a foundation to own and bring these assets all forwards. I hope to see all of you engaging with us in that forum, so we can solve this ever-increasing software complexity problem. So thank you very much for joining me today, and I hope to see you all in person at some point soon.